Hey guys, so in these few set of videos, we are trying to understand the art of the state creation. In the previous video, we already saw how to solve subproblem 1 and subproblem 2 for the dynamic programming. In this video, we will see how to solve subproblem 3 and then how to integrate the subproblem 1, 2 and 3 to end-to-end dynamic programming solution. So if you remember, we were discussing about a directed acyclic graph by the end of the previous video. And we also stated that the importance of directed acyclic graph will become more relevant in when we try to understand the third subproblem of dynamic programming, that is laying down the correct order to solve the states in. So let's just write down whatever we had already solved in subproblem 1 and 2. So basically we had defined dpi was equals to Fibonacci of I, that is dpi represents the nth term of a Fibonacci. No, dpi represents the ith term of a Fibonacci series. And the second point was that is the second subproblem was dpi is equals to dp of I minus 1 plus dp of I minus 2. So basically these were the two subproblems that we had already solved, and the base cases for these two subproblems were dp0 was equals to 0 and dp of 1 was equals to 1. Now let's again draw the same directed acyclic graph that we drew in the previous section. So basically let's draw the graph for dp of 4. So in this case we will have 5 states in total, and the graph will look something like this. All right. So the directed acyclic graph looks something like this for dp of 4. You can draw the same graph for any value of dp, like dp of 10 or 20. It would look just like this. All right. So it's a directed acyclic graph. If you remember, it means it doesn't has any cycle. Now how do we what order should we follow while solving the states? All right. So basically like I said, each state, to compute a state, you need the value for some other states. All right. For example, to compute state number 4, you need the value of state number 3 and state number 2, and that's what this graph actually represents. This directed acyclic graph represents the it's let's say that in the directed acyclic graph is there is an edge from I to j. All right. So this edge I to j, it actually represents, to solve the jth state, you first need to solve the ith state. All right. So the correct order to solve the states will be the topological order of this directed acyclic graph, right? If you sort these states in topological order with the help of this directed acyclic graph, you will get the correct order to solve the states in, right? So for this problem, the correct topological order, it's very obvious. For dp of 4, the correct topological order will be 0, 1, 2, 3 and 4. Why is that? Because you know that you cannot solve second term before solving first and 0. First and 0 are base cases, we don't really need to solve them. You know that you cannot solve the third term before solving the second and first, and you know that you cannot solve the fourth term before solving the third and the second. So you know that first you need to solve the second term, then you need to solve the third term, then you can solve the fourth term. All right. So basically that's why this topological ordering is coming over here, and this topological ordering is the same as the topological sort of this directed acyclic graph over here, and that's why this directed acyclic graph was so relevant over here. All right. So basically if you understand it like this, let's say the graph was not a directed acyclic graph, that is, it had cycles in it. So in that case, you will not be able to sort the states in a correct topological order. And if you think of it like that, that's why while solving a dynamic programming problem, it's very important that the graph that you generate is a directed acyclic graph. All right. Now that we have laid down that, let's just generalize this topological ordering for n states. All right. So the topological ordering for n states will be nothing but 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and up to so on up to n. So it just means first to compute before you compute nth state, you have to compute n minus nth state. Before you compute n minus 1 state, you have to compute n minus second state. So it means that you will start computing the states from dp of 2 onwards, and then up to n, you will compute this in the same order. All right. So for this particular problem, understanding the topological order was very simple, So let's just, now we have all the informations that we needed to code this problem up. All right, so we can integrate these three solutions, and then we can use this to code it. All right, so the third subproblem over here was the finding the correct topological order, and the correct topological order over here is 1 2 3 4 and up to n. All right, now we have solved these three sub problems. Let's see how we actually code this all up. All right, so let's just get into the coding part. All right, so we will do a C++ style whiteboard coding over here for this problem. So let's create a function called int Fibonacci of n. So let's say it computes the nth Fibonacci term and it returns its value. All right, so basically for that, let's just create a dp array. So to solve nth Fibonacci term, we need n plus 1 states in total, if you remember. All right, and then we will initialize the base cases, that is dp of 0 is equals to 0 and dp of 1 is equals to 1. All right, now that we have done these two, all we need to do is we have to iterate over the states in the correct topological order. All right, so if you remember, the correct topological order was 0 1 2 3 4 and up to n. All right, so we already know the value of 0 and 1, so we don't really need to care about these two. All we need to do is iterate from 2 to n. All right, because that is the correct topological order, and we will solve the states in this order. So if for this case, I have to iterate from int I equals to 2, I less than equals to n, I plus plus, and then to solve each state, all you need to do is follow the recurrence relation that we generated in the second subproblem, that is dpi is equals to dp of I minus 1 plus dp of I minus 2. So this was the recurrence relation that we had generated. So we will follow the same recurrence relation over here, that is dpi is equals to dp of I minus 1 plus dp of I minus 2. And then we can return the nth state, that is return dp of n. And this is how you solve a very standard dynamic programming problem. So now moving on ahead, let's just understand the time complexity of this problem. So whenever I calculate the time complexity of a dp problem, I always bear in mind two things. The first thing is the number of states. So in this case, the number of states is equals to n, and the second thing that I bear in mind is the time to calculate each state. So that is O of 1, because the time to compute each state is just this simple addition over here. All right, this simple addition over here is the time to compute each state. So this is O of 1, so the total time to compute each state is O of 1. So the total runtime complexity will be equals to O of n. I hope this was pretty straightforward to understand. Now getting into some other details, one more interesting fact about this Fibonacci problem is, let's say you are given a problem, find the nth Fibonacci number. You can obviously take the dynamic programming approach and it works in linear time, but there is a better approach to solve this problem. So one of the better approaches are, there is an approach called matrix exponentiation. So you might want to check this out. So it not just helps us in solving the Fibonacci series, it helps you in solving a lot of recurrence relations whenever this is applicable, this approach is applicable. So the time complexity to compute the Fibonacci series, the nth term of Fibonacci series to be precise, is O of log n using my matrix exponentiation. So you guys might want to check this approach out as well.